Okay, so at its simplest, and there's many definitions, acidity is a measure of H plus ion concentration or hydrogen ion concentration. So there's a shorthand way to show that, which is H plus in brackets. Since solutions are aqueous or water-based, you can look at this reaction where water can dissociate into a hydrogen ion and a hydroxide ion, and it's reversible. So this can be the reactants to produce this product, or this product can become these reactants. So they go back and forth. These will bond, and then sometimes that covalent bond is so polar that they dissociate, and back and forth. Remember that H plus ions, hydrogen ions, are just protons with no electrons. So in reality, you're going to find them as a hydronium ion, H3O plus. So let me spell that for you. All right, there it is. And in pure water, you're going to find that the hydronium ion concentration is equal to the hydroxide ion concentration, because for every water molecule that dissociated into a proton, there was also a hydroxide, the OH minus, that's hydroxide. There was one of those produced. So their concentrations are equal. And it turns out that at a certain temperature, I think it's 25 degrees Celsius, there's a constant K that is equal to the concentration of the hydrogen ion multiplied by the concentration of the hydroxide ion, and that equals 1 times 10 to the negative 14th. Now remember, those are equal, so that means the hydrogen ion concentration is 1 times 10 to the negative 7. That's pure water. It's a 7. This is where pH of 7 comes from. This is where the 0 to 14 scale of the pH scale comes from. It's actually based on powers of 10. So let's dig into that a little bit more. So when an acid is added to water, it dissociates and forms its ions. Adding water to this equation, we see the hydronium ion is formed. So does hydrogen ion concentration go up or down? We know acids make pH go down, but it seems like hydrogen ions should go up. And if that's what you said, you're correct. This is why. When you're working with negative exponents, the number gets bigger as the exponent gets smaller. So a pH of 5 represents more hydrogen or hydronium ions. In fact, we can visualize the whole pH scale this way. Hydronium ion concentration in moles per liter, that's the concentration units, goes down as we go from 0 to 14. And hydroxide ion concentration goes up. So there is our 1 times 10 to the negative 7 again. Note that at each pH level, the concentrations add up to negative 14. Here's one more way to visualize the change in concentration as you go from 0 to 14. So you can just see more hydronium at a pH of 0 or 1, and then changing to mostly hydroxides as you go towards 14. Most solutions do not exist at the extremes. Definitely in life, we're dealing with things mostly between like 5 and 8. All right, so let's get back to basics again. Remember, it's molecules being added to a solution that are changing the pH and the ion concentrations. So adding an acid like sulfuric acid to water can create hydrogen sulfate ion. There's our hydrogen sulfate ion, and a hydronium. And hydrogen sulfate can act like an acid or a base. So as an acid, it loses another hydrogen and becomes a sulfate ion. And as a base, it would take those hydrogens back, becoming sulfate, hydrogen sulfate, and then sulfuric acid again. The more readily these acids give up their hydrogen and tend to the left side of this equation, the stronger they are. So the more they dissociate, the more they let go of those hydrogen ions, the more hydrogen ions they add, and so the stronger they are as an acid. To understand bases, you need to think back to water. And you need to know that adding hydrogen ions or hydroxide ions will tip the equilibrium of this reaction. So from this, back to creating water. So that's why you have this reversible reaction symbol here. So when a strong base, like, for example, sodium hydroxide, is added to water, some of the hydroxide ions will bind with H plus and create water. This removes H plus from the solution, creates more water, and increases the pH above 7 into the range where we call something a solution a basic solution. And sometimes an ion can act like a base. This is a reaction of carbonate with water to form bicarbonate ions. Here, carbonate acts like the base and takes hydrogen from water, leaving hydroxide ions and bicarbonate ions. Not shown is that the bicarbonate ion can actually take up more hydrogen ions from this aqueous solution and form carbonic acid. These molecules are weak acids and bases. They don't dissociate fully, and they can buffer against big changes in pH. So for more on buffers, see my video on the bicarbonate buffer system. I actually use some of these molecules, but I look at the full spectrum of what they can become as they dissociate or take these molecules, these ions, out of solution. So in conclusion, you can find these ions just about everywhere, especially in the body. Acids increase the hydrogen ion concentration and bases decrease the hydrogen ion concentration. So more hydrogen ions, more acidic, but a lower pH value. Less hydrogen ions, more basic, higher pH value. And hopefully that helps you kind of get your head wrapped around acids and bases.